Okay, let's discuss in the next few videos, in this and the next few videos, analog to digital converters. Okay, in this video, I just want to kind of introduce the idea of analog to digital conversion, which I'm sure is not new for you. We have talked about it a few times before as well, but I think it's good to kind of go over the basics again. So, what does an analog to digital converter do? It takes an analog value and it converts it into a digital output. And uh, the relationship between the analog value and there is a relationship between these two, and we essentially want a proportional relationship, right? So the input output characteristic of an analog to digital converter is shown here on this slide. So on the x-axis we have analog input, and on the y-axis we have the digital output. You can see what we are doing basically in an analog to digital converter is taking the analog input, which goes in this case from 0 to some value, which probably is 8 delta, right? And then you divide the analog input into various uh, parts, various intervals, and then you assign each interval a particular digital code. So that's what we want to do as a part of your analog to digital conversion. And we've discussed what analog to digital conversion actually involves uh, uh, in terms of the steps that are involved in the conversion. It involves sampling, quantizing, and coding. And here we are basically talking about quantizing and coding, right? You take an analog value, you look at where the interval, in which interval it lies, and then give a digital code or a digital output to that. Now, of course, in this case, the digital output is basically 2 to the power m times a, which is your analog value, divided by vref, where vref is basically the range of your analog input that you can give, right? So the each interval here, delta, is vref over 2 to the power m. Okay. If we think about what kind of error we get when we do this kind of quantization, you can see that the error when you are very close to a boundary, just at the starting of a particular interval, is 0. And then as you go towards the end of the interval, the error actually keeps increasing, right? So this was the analog input, but you're representing it with a number that is 010. So there is a large error as we go towards the uh, end of the interval. Now, we have mentioned this before. Analog to digital conversion, this quantization that we are doing here is lossy. You'll always have some error, uh, but what you can and you can't help it, right? You can model this error with the analog to digital converter as if there was a noise being added to your signal. Okay, so this quantization error can be modeled as a noise. So you have your signal, and on top of it, we add a noise, which is basically the errors because of the quantization process. And if we do that, we can calculate something called the signal to noise ratio. The signal to noise ratio is basically the signal power divided by the noise power. If a signal has no noise, then the noise power becomes 0 and the signal to noise ratio becomes infinite, right? Because there's only signal and no noise. Of course, that's not practical in real signals. Uh, However, the higher the SNR or the signal to noise ratio, the better it is. For uh, analog to digital conversion, the signal to noise ratio, the peak signal to noise ratio, is given by the formula here on the screen. Usually, we write a signal to noise ratio in logarithmic terms. We write it in dB, and this is the ratio that we get. As you can see, if you increase the m, which is the number of bits of the analog to digital conversion, you get a higher and higher SNR. And that's what you expect, right? So if you have, so this is a 8-bit analog to digital converter. If you instead use a 16-bit analog to digital converter, you would find that the intervals are smaller, which means that your quantization error is going to be smaller. It's not going to be as large as this. And therefore, the signal to noise ratio would be higher.